Okay, so Assalamu alaikum everyone, and welcome to the seventh lecture, which is our second last lecture today. As I've posted in the uh, Google Classroom, we hope to take a group photo, or to be more precise, a screenshot together. So we'll really appreciate if you switch on your video at the end of the lecture tomorrow. So again, we're very grateful to all of you for the interest you've shown throughout the series, and we sincerely hope that you've actually learned something from these. So that's all the introduction from my side, and now Dr. Sabi will begin with his lecture.
All right. Assalamu alaikum, everyone. Once again, after a break of 6 days, we are meeting again. It's really heartening to see people who stick on to the seventh lecture, who persevere and conserve their energies and their interests remain somewhat intact so that they are here for the seventh lecture on quantum computing. So we've covered a lot of ground in the first six lectures. We've looked at the nature of quantum information. How do we represent quantum states? How do these states transform with time or by the action of certain quantum logic gates? How do we represent states, as well as the representation of dynamics was also investigated. So all in all, with the help of this background, we were able to look at a particular quantum algorithm, and we saw how the problem of measurement in quantum mechanics, which collapses quantum states, can be bypassed by encoding quantum information in special ways and encoding your problem into a special kind of unitary transform so that our measurement results yield answers to desired questions or promises. So one has to massage the entire problem of that you would like to tackle into a quantum setting, and quantum mechanics allows you to do that. Then we also looked at the concept of entanglement and saw how entanglement is so unusual and eerie and strange when compared to classical information. We also saw how quantum entanglement could be used as a resource for teleporting quantum states. Then in the last lecture, I also gave you a problem of quantum error correction. So all in all, we've covered a lot of ground. But still we've only barely scratched the landscape of the field of quantum computing and quantum information. Um, so are there any questions before I proceed with today's discussion, which will primarily be focused on the concept of non-locality and its relationship with quantum communication? So some more strange ideas coming our way today. So are there any questions?
Assalamu alaikum, sir.
Walaikum salam.
Sir, I have.
I have a question.
Okay, you could go first.
You can ask.
Okay, thank you. Okay, I missed the lecture on Saturday the last time, so I went through it, and I'm just a bit confused about what the difference between a mixed state is and a state which is not maximally entangled. In particular, if you could, give some physical examples, maybe it could help me better understand what the difference, or are they the same things? Thank you.
Well, so we have two kinds of quantum states. One are the pure quantum states, and the other are mixed quantum states. States that can be written in the form of psi, a ket, or vectors, they are called pure quantum states. In this course, we've only looked at pure quantum states. And pure quantum states have they have zero information content. They are totally deterministic in the sense that suppose I say I tell you that the sun rises in the east, and when I say this statement does not give you any new information. It's a pure statement. However, If I provide you an information such that you're on the planet of Jupiter, and you would like to say that one of the Jovian moons rises, and I just say that the Jovian moon rises, and I don't provide you with the information whether it rises in the east or west, then this simple statement, the Jovian moon rises, has a lot of information in it. It has, in fact, 2 bits of information in it, whether the moon rises in the east or in the west. Okay, so we say that the uh, statement that the moon of the Jupiter rises, barely this statement has 2 bits of information in it, because unless you make a measurement and you find out for yourself and you make a discovery that the moon rises in the east or the west, you don't know anything about the direction of the moon rising. So the entropy of this statement is maximal, or there is complete lack of knowledge until and unless you've made a measurement. So these are mixed states. So a pure quantum state is a state which can be written as ket psi. Now, if I have 2 qubits, then this state psi could be, for example, ket 0, ket 0. This is also a pure quantum state. The state could be 1 over under root 2, ket 0, ket 1 plus ket 1, ket 0. This is also a pure quantum state. And it happens to be an entangled state as well. Okay, so any state which is pure has zero entropy. It has no information content in it. Just by looking at how you write the quantum state, you can you can decipher all that could be known about the quantum state. It's like saying that the sun rises in the east. You already knew it, and having hearing this statement will not add extra information to your body of knowledge. However, if I have a state which is which I'm totally ignorant of, and it's hard to characterize that state, then such a state is called a mixed quantum state. And a property of a mixed quantum state is that it cannot be written as a ket. It can't be written as a ket. Rather, it's written in the form of another object, which is called a density operator or a density matrix. All right. So if I have, say, a box, and I looked at this example in the previous class as well, one of the previous classes, in which I have a combination of spheres, and some of these spheres are purple, and some of them are plain white. Okay. Now, if I were to pick out one sphere or one ball from this box, and I keep my eyes shut and I don't look at the color of this box, I would like to know what is the state of that box, whether it is purple or whether it is white. I have no information, no clue whatsoever of what the state of this ball is going to be. Therefore, I would like to write a state. I would like to prescribe a state to this ball. And the state that I would like to prescribe is that this ball could either be a purple ball or a white ball. And the way of writing this state is that I would write a density matrix for the state of a single ball. And that state would be rho equals purple ket purple, bra purple, plus ket white, bra white. And if there are equal number of white and purple balls in this box, I would write a factor of 1/2 with each one of these states. Now these are states, and they are not being written as kets, rather they are being written as a combination of ket and bra, which is called an outer product, slightly different from an inner product. And with each outer product, there is a coefficient. If there's a coefficient p with this operator, There's a coefficient 1 minus p with this. So p is like a probability. And this is an a priori probability. Therefore, if I take a quantum state and then I were to take another particle in a different quantum state and mix the two together, I get a collection of particles. That collection of particles can also be called an ensemble of particles. Now, is that collection of particles defined by a state? Yes, of course, it's defined by a state. And if I were to choose one box or one sphere from that box, just one sphere, then I can also ascribe a quantum state to that sphere. And in quantum mechanical terms, if these are quantum mechanical properties, the sphere is not either purple or white. It's an incoherent mixture of both, because the information that it contains is that there is a certain probability that if you would measure the color of this ball, it could turn out to be purple or it could be turn out to be white. So you will ascribe or write a density matrix with each ball. And that density matrix is not going to be a superposition of purple and white. Rather, it is going to be a mixture, an incoherent mixture of purple balls and white balls. So each ball in itself will carry a density matrix with itself. Okay, so this is an impure quantum state, okay, or a mixed quantum state. And you can imagine in simple word that this is a totally random quantum state, whereas a pure quantum state, even a superposition of this kind, if I were to write a superposition, this quantum state over here is not a mixed quantum state. This does not have cat 0 mixed in with cat 1. It is a pure quantum state. It is a coherent mixture. There is some phase relationship between the two basis states. I can choose another basis, any other basis, and I can write in that basis this quantum state in another form, say cat plus. All right. So I can always choose the basis or reorient the basis to represent a cat as another cat, but still all of them remain cats. Okay. So this is the basic difference between a pure state and a mixed state. And a pure entangled state is one of this kind. For example, in 2 qubits, this is a pure entangled state, an example of a Bell state. If I just look at 1 qubit, just Alice's qubit, it's going to be totally random. So the density matrix of a single qubit, when looked at alone, is going to be maximally mixed or as random as it can get. So a subsystem of a maximally entangled pure state is a maximally mixed state.
Ah,
I hope I've tried to answer your question.
yes, sir. Thank you.
Okay, there was another question.
Yes, please. I have two questions. The first one is what we can do as a second step on quantum computing. And
Like,
the second question,
oh, let's first do the first question. So, can you repeat your question?
what we can do as a second step on quantum computing.
So, you want to learn more about quantum computing?
Yes.
Okay. So, as a second step, uh, so there are different ways you could look at quantum computing. You could look at it from the physics perspective, which means you could look at particular, say, implementations. How do we build quantum computers physically in the lab? You can build them with photons, you could build them with squids, you could build them with electron spins, you could build them with nuclear spins, and so on. So this requires a good working knowledge of physics, atomic physics perhaps, condensed matter physics in many cases. You could look at also NV centers in diamond. Okay. So one approach is to look at it from the perspective of physics. The other approach is to look at it from the perspective of information theory. So one is physics, the other is information theory. In information theory, you could look at concepts of how do we measure entanglement, how does how do quantum effects help in quantum communication, how much information can be transferred in a quantum channel versus a classical channel, what is the role of noise and decoherence. So if you would like to transmit a quantum message to a quantum satellite, as China is doing, what are the probabilities that your signal will be corrupted, or there will be some hijacker who can intercept your signal and corrupt the signal. Then there are deep mathematical problems in information theory as well. When you deal with large qubits, large numbers of qubits, you want to break the quantum ascendancy limit by having a quantum computer with 50 or more qubits. Then how do we characterize entanglement in these systems? And how do we a major problem, a physics problem, is measurement. How do we measure in such large systems? So there are different ideas. Then you could also look at it from the perspective of pure quantum programming. Now there are open source quantum computers available, which can be logged into by users from all over the world, and you can use a particular language similar to C, and you could write a program, and your program could run on a quantum computer. So you could learn quantum programming. You could simulate quantum computers for 2 or 3 qubits on your classical computer as well, in Mathematica or MATLAB or Maple. So there's the whole idea of quantum programming. And in quantum programming, you also have to write and devise new algorithms. So I I gave an example of a Deutsch algorithm. There are other algorithms like Simon's algorithm, like Grover's search algorithm, Shor's algorithm, which helps factorize numbers. So you there is, by the way, a dearth of problems that can be solved by quantum computing. So looking at new problems and devising new problems that could be cast into quantum language is really important. And finally, there's a lot of applied research in quantum computers that is going on. For example, if you would like to design a new drug or make a new molecule that treats the corona vaccine, the COVID-19 virus, then you would need, since these molecules and these proteins work according to the laws of quantum mechanics, as every small molecule or atom should, then you could come up with a quantum simulation of for these drugs and these molecules. How do these drugs interact with your targets in the human body? So there's a lot of potential as far as the applied science is concerned. Quantum computers will really help in e-commerce as well. So all of these are various directions that could be explored after you've taken this first course on quantum computing. I hope I've understood your question correctly and I've answered it also to your desire.
Thank you very much.
Is there a second question as well?
Yes.
Yes,
Uh,
please.
what's the benefits of knowing this information as a student?
Right. So first of all is the benefit of gaining knowledge. Rabbi Zidni ilma. So is one is the increase of knowledge, which is a benefit in itself. It increases our awareness about our natural world. We know more about our natural world, about how systems, atomic systems, molecular systems, small systems, and cold systems, they generally follow the rules of quantum mechanics. So we know more about our universe, more about our natural surroundings, about how these small microsystems work. The second is, as a student, you will notice that many new jobs and employments in the future will be in the realm of quantum technologies, quantum computing, and quantum information. For example, back in the 1970s and the 1960s, there was a space race between different countries. Both Soviet Union and the United States wanted to send their missions to the moon and to the outer space. So there was a flurry of activity and a lot of jobs were created, a lot of employment was created, a lot of competition arose because of the space age. Likewise, in the year 2000, the Human Genome Project was nahin. The Human Genome Project was cracked. So we had a genetic code or a genetic deciphering of the whole genome of the human race. That kick-started a flurry of activity in genomics and genetics and microbiology and medicine and personalized medicine. Likewise, in the year 2020 and onwards, I think the next 10-15 years will be very ripe for quantum technologies, be it for information transfer, be it for communication, be it even for warfare and strategic initiatives. So I think there will be a lot of market that is available in the realm of quantum technologies. And the benefit to students, of course, is that equipped with this knowledge and with this understanding, they will be able to uh, go into these new areas and do something for their countries. They can be the pioneers, because this is an area which is very less developed in the developing world. So I think there's a lot of potential for students. And the third thing I would like to say, the quantum computing and quantum information is a paradigm shift. It shifts our understanding from the Newtonian world to a post-Newtonian, to a quantum world. It gives us different concepts of the world. And I'll give you one or two examples today when I talk about non-locality, something really counterintuitive. So those students will be in those small veneer, small section of students who actually think beyond the classical world. So I think these three advantages are big enough advantages for any student, be it from engineering, from physics or computer science, to look at quantum computing with some level of seriousness.
Yes, thanks a lot.
All right, so I think let's start. Oh, is there one more question? Or? Yes, Madiha.
Uh, Assalamu alaikum. I have just in the continuation of Sajda's question. First, you mentioned there are tools to develop and check your algorithms on quantum computers. I know one that is IBM Quantum Experience. What software or what quantum computer experience do you suggest to start for programming for the beginners? Number one. And number two, while I was researching, I'm just a beginner in this field. And when I started off, there were certain papers which were dealing with the emulations of the basic quantum gates on FPGAs or ASICs or anything. So what do you think that is that field prosperous or not? Emulation of quantum computing on classical computers.
So by definition, the emulation of classical quantum computers and classical computers will not cannot take place, because one requires polynomial amount of resources and the other requires exponential amount of resources. You might be able to emulate small quantum computation tasks on a classical computer, but nothing really useful and nothing really big. So I think there's not much scope in emulation. For learning purposes, if you want to build a 2 or 3 quantum computer and you would like to simulate it on your classical desktop machine, then it might work. As far as programming languages are concerned, I think Q Sharp is really good. There are other candidates out there, and there are some open source um softwares as well. And we might want to do another course on computing with programming with another instructor. But it all depends upon your prior background. If you are trained in Python or Java or C, or some high level programming language or a low level programming language, so there are different variants out there.
Thank you so much. I would like to request the platform of Cakes and you that if there's any chance of organizing such a seminar in which we can actually do hands-on programming on what we learned in this session, it would be great. I guess I'm saying on the behalf of the whole class.
I think we'll try, inshallah. We'll try, inshallah. So just give me a second, I need to close the door. Just give me a second. All right, so let's start discussion a little bit on non-locality, if you allow, because this is a really important concept. And this concept is not only important for quantum communication, it's a hallmark of quantum information and quantum computing. It's like a characteristic trait which distinguishes quantum mechanics from classical mechanics and quantum information from classical information. So it's going to be, I'll give two examples of non-locality, and I hope I can cover both of these examples in the in these in this half an hour. So suppose I have two parties, Alice and Bob. And each of these parties has a box, a simple box. And each box has an input. Alice has an input X. Bob has an input Y. And each of these inputs could be 0 or 1. So Y could be 0 or 1 and X could be 0 or 1. And the boxes are really simple. So they not only have an input, some processing takes place inside the box and some output is given. Suppose the output of Alice's box is A and the output of Bob's box is B. Okay. And each one of these A's and B's could be from 0 and 1. So A could be 0 or 1 and B could be 0 or 1. So binary inputs, binary outputs. Okay. And there is a certain probability. So I represent probabilities now by capital P. There's a certain probability that Alice's output is A given an input X. This is how I write conditional probabilities. That is, if Alice's input is X, this is the input, then we would like to find out the probability that the output is A, which could be 0 or 1. Likewise, I can define probabilities of getting the output B on Bob's box with an input Y. Okay. Now let's play a game. Okay, we would like to play a game. Both Alice and Bob are together and they would like to play a game. And what is the game? And they want to win the game. So what is the criterion of winning the game? The criterion for winning the game is that they win the game if the exclusive OR of A and B is equal to XY. X multiplied by Y. Okay. So this is the criterion for winning the game. Now, let's first define, you already know what the exclusive OR means. So if I have A and B, and I would like to find the addition modulo 2 of A and B, this is how this truth table is defined. If both are 0, the output is 0. Either one is 1, the output is 1. And if both are 1, the output is 0. So this is how we define the exclusive OR gate. So the game that they would like to play is that the inputs X and Y, when they're multiplied together, they yield an output. The product X and Y is equal to the exclusive OR of A and B. So A and B should be such that when you take the addition modulo of 2 of A and B, the answer is equal to X multiplied by Y. Okay. So now Alice and Bob live together for some time and they share a protocol. Okay. They share a protocol or they share rules of the game. The protocol are the rules of the game. Excuse me. So they have to devise or design the rules of the game. Okay. And then when they have designed the rules of the game, they go far apart. really far apart so that they do not communicate with one another. They are spatially separated. Okay. And at the end of the game, they collect their results and get together and share the results and see whether they have won the game or not. Okay. So this is the scheme of affairs that we're talking about. So let's first try to come up with a protocol that they need to devise. So the key is that A addition modulo B modulo 2 is equal to X product with Y. So let's look at the possibilities. Let's decide some rules. Alice and Bob. Suppose Alex says that if her input is 0, she decides that her box will produce 0. She decides that. Okay. Now Bob is sitting next to Alice. Okay. So Bob tells Alice, okay, so this is what you've decided. Let's write down this rule for you. Now, how I would like to respond is that if my input is 0, my output B should be 0 as well. Because having this set, having this set here will ensure, together with this rule, that if I multiply x with y, I get 0, and a plus b modulo 2 is also 0. So this rule is going to be satisfied. Okay. So Bob has to come up with this scheme. Now Bob has two possible inputs. So Bob tells Alice, okay, let me write the other rule. Let's take turns, and this time I'm going to write the second rule. My second input possibility is that I might input in my box y equals 1. So if this is the case, and I need to be compatible with Alice's rule, x equals 0 and a equals 0, then my b must equal 1 so that we win this game. Okay, so these three rules are defined. Okay, so now once we've defined these three rules, Alice has to come up with the fourth rule so that everything remains intact. So what she does is she says, okay, her second possibility is that x equals 1. And when x equals 1, she says, okay, if I were to be compatible with this rule, I need a equals 0, because then I will ensure that this rule here is satisfied, because x multiplied by y equals 1, a plus b should be equal to 1, and that is only possible when a equals 0, because 0 plus 1 modulo 2 is 1. But the problem is that if Alice sets up this rule and Bob's input is y equals 0 and Alice's input is y equals 1, their product should equal 0, but a plus b modulo 2 turns out to be 0. So for a combination in which this happens and this happens, Alice and Bob lose the game. All right. So what's the probability of their success? How many times do they, if they now separate out, go far apart and play this game, sometimes the input is 0, sometimes the input is 1 on each box, and they write down their outputs, what is the probability that they will win the game? How many times will they win the game and how many times will they lose the game if they come up with this set of rules? So anyone with an answer?
50% of the time they win, 50% of the time they lose.
They will win 75% of the times, because they will win when Okay, they will win when this condition, sorry, and this condition is satisfied. They will win when this condition and this condition is satisfied. All right, and they will also win when this condition and this condition is satisfied. So they will win 75% of the times, and they will lose 1 out of 4. They will win 3 out of 4 and they will lose 1 out of 4. So is this clear?
Yes, thank you.
Yeah. So the probability of success.
Doctor, the first box and the third box, A exclusive OR with B will give you 1, but X times Y will give you 0.
Yeah, so then they will lose. Then they will lose. So
Yes,
they
they
can
will
only, yeah, they can only win 75% of the times. So the probability of their success is 3 by 4. Okay. And the probability of their failure is 1 by 4. So the probability of success is 3 by 4. Probability of failure is 1 by 4. And this is when we have a classical case and no communication can take place after Bob and Alice have gone apart. Okay, they have devised a rule, they have come up with a protocol, and they go apart. And then they do not change the rules in between. They are honest people. Now, so can we increase the probability of success? Let's do another, let's come up with another set of rules. Let's see if we can increase the probability of success. So this is Alice's set of rules. This is Bob's template. Okay. So likewise, Alice sets x equals 0, a equals 0. Bob has to set y equals 0, b equals 0. Then if y equals 1, Bob's b must be equal to 1. Now Alice takes a different route. She says that if her x equals 1, her a, instead of being 0 here, let's put it equal to 1. Because what that does is that it satisfies the winning of the game for these two scenarios. That is x multiplied by y, 1 multiplied by 0 is 0. And so it satisfies, does it satisfy any condition? So if x equals 1, y equals 1, x multiplied by y equals 1, a plus b, 1 plus 1 is 0. So this is not satisfied. However, if x equals 1, y equals 0, the product equals 0 and a plus b equals 1. So this isn't satisfied either. Okay. So the maximum probability of success is given by this scenario here. It's 3 by 4. Okay. So this is the maximum probability of success that is achievable in this classical scenario. Now we would like to see if quantum mechanics helps us. And can we break this barrier here? So this barrier is an example of what is called a Bell's inequality. And we will see how quantum mechanics can cross this barrier, how it can violate this inequality. All right. So in order to do that, we have to do something more interesting. So any questions about this classical maximal probability of 3 by 4? Alice and Bob both devise a game, they design the rules of the game, but whatever rules they design, the probability of success does not go beyond 75%. Okay. So now suppose Alice and Bob both have some Each one of them has a box, but now their particles are quantum particles. And inside the boxes, they do some quantum processes and they do a measurement and they yield an output. Once again, the output is A and the output is B here. The only difference is that this could be a cat A, this could be a cat B, and each one of them is 0 or 1. So the output could be cat 0 or cat 1. Now, is it possible to break this or violate this probability of success and go even higher with quantum states and quantum dynamics and measurements? Indeed, it is possible. And this was first shown by a scientist in 1964 by the name of John Bell. And how does it work? It works in the following fashion. If Alice and Bob, they share a Bell state, which means that the state that they share is given by 1 over under root 2 cat 0 Alice on Alice's qubit and cat 0 on Bob's qubit plus cat 1 on Alice's and cat 1 on Bob. So two particles come together and they are entangled with one another, right? And they are brought into this state over here. And then when one particle goes to Alice and the other particle goes to Bob. So now they share one of the entangled pair of particles. And now they come up with a rule, a different kind of rule. And each one of them says the rule is slightly complicated, but not that much complicated. They say Alice has two possible inputs, 0 and 1. So Alice says that if her input is 0, she will measure her qubit in the cat 0, cat 1 basis. So what this means that if we were talking about photons, and this is Alice's experiment, if the signal that comes to her is that her input is X is 0, then she decides to use a polarizing beam splitter, which separates out the photon and channels it into the cat 0 channel and to the cat 1 channel, and then performs a measurement. However, if her input X is the state cat 1, she still uses a polarizing beam splitter. So her input is now X equals 1, but her polarizing beam splitter is now a different kind of polarizing beam splitter. So I would like to draw it with a different color perhaps. It's still a polarizing beam splitter, but its two output beams are not cat 0 and cat 1. Rather, they are, say, one channel is 0 plus 1 over under root 2 and the other channel is 0 minus 1 over under root 2. And she does a measurement. Okay, so she changes her basis depending upon whether the input is 0 or 1. So if I were to draw this basis, so I can, in shorthand, this state 0 plus 1, I can write as 45 degrees. So it's an equal mixture. It's not a mixture. It has a coefficient 1 over under root 2 here and 1 over under root 2 here. And 1 over under 2 is cosine of 45 degrees. So her basis is now rotated. One basis state is cat 45. The other basis state is 90 plus 45, which is 135 degrees. So now her basis has changed altogether. And she tells this to Bob. Bob knows about it. Likewise, Bob is also clever, and he has also learned some physics and quantum mechanics and quantum information. And what Bob does is also chooses between two states. So if Bob's input is 0 or 1, so if Bob's input is 0, the state that he chooses, the basis that he chooses in which he would like to make a measurement is 22.5 degrees, which is pi by 8, half of pi by 4, and 90 plus 22.5, which is 112.5 degrees. And if his input y were 1, Bob chooses his measurement basis to be minus 22.5 degrees and 67.5 degrees. Okay. Now Alice and Bob choose their bases depending upon what their inputs are. Alice can randomly get 0 and 1 as their input, and whenever she gets a 0, she chooses this as her basis. And whenever she gets 1 as an input, she chooses this as the basis. Likewise, Bob switches between these two bases depending upon the value of phi. Okay. Now Alice and Bob have devised this rule. So remember that if I look at this experiment here, the some input is coming in cat phi, either this channel is going to fire or this channel is going to fire. Okay. And if this channel fires, the horizontal transmit channel fires, the classical result A or B, whatever the case is 0. And if this channel fires, the classical result is 1. So this is how the classical 0 and Y, the outputs A and B are defined. All right. So now these are the rules of the game. All right. Any questions about this? Because what we would like to see is whether this protocol can yield a probability of success that is greater than the classical result of 75%. Now, any questions about the game or the rules of the game? Because this is slightly tedious and cumbersome. Though once you understand it, you get the hang of it. But still, is there any question? All right. So depending upon the input X or Y, Alice and Bob switch or toggle between two possible measurement bases. So they change their bases depending upon what the input are. But both of them know for sure deterministically that if I were to get X equals 0, this is the basis I'm going to use for measurement. If I were to get X equals 1, this would be the basis. All right. Now what we would like to do is we could make a table. And this is something that you should do as a homework, and I could see the results tomorrow. The table that you would like to make is of this kind. So so the input could be 0 and 0. And for these two inputs, there could be 4 combinations of A and B. You could get 0, 0, 0, 1, 1, 0, 1, 1. But the input could be 0 and 1. The inputs are totally random. And here in the third and fourth column, here and here, I'm writing all the possible output states. 0, 0, 0, 1, 1, 0, 1, 1. 1, 0, 0, 0, 0, 1, 1, 0, 1, 1. 1, 1, 0, 0, 0, 1, 1, 0, 1, 1. All right, now let's see which one of them leads to a success and which one of them leads to a failure. The rule of the game is xy equals a plus b modulo 2. So xy here is 0. So this is a success. I show success by tick. This is a failure, failure, success. Okay. Likewise, the product xy is again 0. This will be a success, failure, failure, success. Now here the product is again 0. This is once again a success, failure, failure, success. Here xy equals 1. Now, can anyone tell me what this first row is going to be? Is this going to be a success or a failure?
Failure.
Failure.
Failure. Then
Success.
hmm,
Success. Failure.
Failure, success.
failure,
Yes.
right? So let me just zoom this out a little bit. So I would like to find out. So there are 16 possible outcomes, and I would like to find out the probability of each event. Okay. So I'm more interested in finding out the probability here of this, and the probability 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 of this, and this, and this. And then I would like to add up all the probabilities and see what the total probability is going to be, and whether that probability is equal to 75% or whether I can violate the 75% condition. So how do we find out probabilities? Finding out probabilities is rather easy. We already took inner products. So let's compute just one of them or two of them and see what the result is going to be. So I'm going to compute the probability of this thing. I'm going to show you how explicitly this is done. So, all right, let's do this. So I like to compute the probability that if my x is 0 and y is 0, then what is the probability that both my a is 0 and b is 0? Okay, so this is what I would like to calculate. So given inputs, each one of them equals 0, what is the probability that I get 0 as the output on A and B as the output on Bob? B equals 0 as the output with Bob. So x equals 0 on Alice means that she uses a basis which is 0 degrees and 90 degrees, or 0 and 1, and Bob uses a basis which is 22.5 degrees and 112.5 degrees. And the outputs are A equals 0, which means the output vector lies along this axis, and B equals 0, which means that the output vector lies along this axis. Okay, so it's on the 0 channel here, 0 degree channel here, and it's on the 22.5 degree channel with Bob. So I would like to find out the probability of this event occurring. And how do I do that? I take this quantum state 1 over under root 2, get 0, 0 plus 1, 1, and I find the overlap with the outputs. Now Alice's output is get 0. I can write 0 or 0 degrees, it doesn't matter. And Bob's output is 22.5 degrees. So I put this in bra form and take the modulus square. This will be the probability that I desire over here. Okay. So if I were to do this computation, this 1 over under root 2 square, this comes out of the bracket. This bra gets connected with this cat bra 0, cat 0. This bra gets connected with this cat, 22.5 degrees overlap with 0 plus 0, 1, 22.5, 1. And then I need to take the square of this, modulus square of this. Now, automatically, you will observe that this thing is 0. So I just ignore this factor here. This is 1. Now I need to calculate the overlap of ket 0, which is pointing here, with ket 22.5 degrees. So this is 0 degrees. This is ket 22.5 degrees. Now, in order to find the overlap, the projection, the overlap is just a projection. This is cosine of pi by 8 or 22.5 degrees. I square it, cosine square, 1/2. So this is the probability that I desire to find. And this probability, I can just put it back in here. It's going to be 1/2 cosine square pi by 8. Now you can do as a what you could do as a homework is that this probability turns out to be 0. This probability turns out to be 0. This turns out to be 1/2 cosine square pi by 8. I get 1/2 cosine square pi by 8 here. 0, 0, 1/2 cosine square pi by 8. And all other probabilities turn out to be 0. And you can do this as a homework. All right. So just as an example, probably I should show as an example. Let's find out this probability here. That is when x and y are both 0, a is 1, b is 0. What is the probability? Let's find this out so that you can convince that I'm not lying here. I'm just trying to save time. And so the probability that given x equals 0, y equals 0, I would like to find out the probability that a equals 1 and b equals 0, a equals 1 and b equals 0. Once again, the basis that Alice and Bob are using is the following. Alice uses the 0, 90 degrees basis. And Bob uses the 22.5, 112.5 degrees basis. Okay, let's compute this probability. So I write down the state. And now A yields 1, which means that my output state is the output channel is along here, right? 90 degrees, which in my shorthand is 1 for Alice, bra 1, and B, I still get 0. So my bra for Bob is going to be 22.5 degrees here. Then I take the modulus square of this. So I get 1/2. Let's see what's happening. Bra 1, ket 0, 22.5 ket 0 plus bra 1, ket 1, and then bra 22.5 ket 1. One zero. All right, just let me just check this. A0. So this thing turns out to be modulus square. This thing turns out to be 0. Okay, so I don't need to calculate it. This thing turns out to be 1. And this thing turns out to be cosine square. And the angle is between 90 degrees and 22.5 is 3 pi by 8. I get 1/2 here. So this is the probability that I need to write over here. So I'm just gonna, what I'm trying to do is, these probabilities are not 0. Sorry, these probabilities are not 0. They turn out to be something else. This probability is, we've just calculated half cosine square 3 pi by 8. This probability I think will also be 1/2 cosine square 5 pi by 8. And these probabilities would also be different. But I'm not concerned with these probabilities. I don't have to calculate these probabilities because these are failures anyway. And I'm just interested in calculating the probability of success. So there are 8 successes in this table, 8 tick marks. 1, 2, 3, 4, 5, 6, 7, 8. So the probability of this success is 1/2 cosine squared pi by 8. The probability of this success is 1/2 cosine squared pi by 8. This is also the same. This is also the same. And it turns out that the probability of this event happening is 0. Probability of this event happening is 0. And this I would like you to do as a homework. And the other probabilities, they are non-zero as well. But I do not want to calculate them and waste my time calculating them because I'm only interested in finding out the probability of success. And when I find out the 4 probability of successes and I add them up, the total probability of success with an entangled quantum state and no classical communication, once Alice and Bob have devised the rule that they're going to toggle their bases depending upon x and y, the probability of success is 1/2 cosine square pi by 8 4 times, because there are 4 successes with non-zero probabilities. And if I were to calculate all of this, what I would get is 2 cosine square pi by 8. And 2 cosine square pi by 8 I know is 1 plus cosine pi by 4. Okay, I just use a trigonometric identity here. This is 1 plus cosine pi by 4. So this is just a minute. Sorry, just a minute. This is plus cosine pi by 4. This is 1 plus 1 over under root 2. Oh, I'm sorry. So this becomes 1 over under root 2. 1. So I think I'm missing a factor here. I'm missing some factor here. I might be doing a mistake. This should really be cosine. So I'll get back to you about the mistake that I'm doing, but this shouldn't be as 2 here. So I'll get back to you with this. So the answer probability of success turns out to be cosine square pi by 8. And this is 1 half 1 plus cosine pi by 4. So the formula is cosine theta by 2. Cosine square theta by 2 is 1 plus cosine theta over 2. And this turns out to be uh, so I can write this as 1 half 1 plus 1 over under root 2, 1 by 4, 2 plus 2 under root 2. This is 1 by 4, 2 plus under root 2. This is 2 plus under root 2 over 4. And the other result that we had in the classical case was 3 by 4, which is 2 plus 1 over 4. And this, of course, is greater than the classical result. So in the quantum realm, using entangled states, we can violate Bell's inequality. So any questions about this? So I'll just do the algebra correctly and I will send you the final result after this class, but this is the basic essence of this calculation. So would you like to ask any question here? And probably try to do this as a homework. Yes. Yes, Ran Jibreen, please ask the question. Does the input in the classical case have to be classical? So what we're trying to do is we're trying to compare quantum with classical. In the classical world, our inputs are going to be bits. Even in the quantum world, when we're talking about the quantum world, the inputs are classical bits, zeros and ones. And depending upon zeros and ones, the states are quantum, but the information that comes into the box and goes out of the box always remains classical. Okay, so the quantum world does not mean quantum information coming in and quantum information coming out. It means that the particles are quantum mechanical and they are shared by Alice and Bob, but the information that is beamed into the box, X and Y, they're classical bits of information. And the information that goes out of the box, oozes out of the box, A and B, that is also classical information, 0 and Y, 0 and 1. So outside, so we have a box. So we have a box. The information that comes in is classical, and that is 0 or a 1. And the information that goes out, which is A or B, is also classical. But the particles that are coming in each of the box, this is the quantum particle. Okay. So we've seen that if the particles are quantum mechanical and quantum mechanical measurements are allowed, which are of the projection kind, then it is possible to break the classical limit of the success of winning the games, the success for winning the game, which is 75%. And still, once Alice and Bob have decided on a protocol or a rule for the game, they do not share any classical information. They go separate out into separate worlds, separate planets, separate continents. They never tell one another what their inputs are, X and Y. And however, they have chosen the basis after mutual consultation. And once they follow and stick to the protocol that they've already decided, it turns out that the probability of winning the game has gone up. Of course, if you allow classical communication, that is, if Alice tells what her input is and she tells what her output is and she calls up Bob, Bob can always adjust her output depending upon his input and the information he's received from Alice and adjust her output, his output, so that the winning probability of winning the game can become 100% if classical communication is allowed. But we're not allowing the two parties to communicate once they have separated out. And this is why this phenomenon is called non-locality. Even though the boxes have gone further apart, there is some correlation between the outputs which goes beyond, which is stronger than the classically predicted correlation. This is quantum non-locality. And there is a certain inequality that has come up, which is 75%, which is violated in the quantum mechanical case, which means that quantum mechanics is violating local realism, or quantum mechanics is perfectly non-local. And remember, it's non-local, but it does not violate special relativity because no information is really traveling between Alice and Bob. There's no superluminal communication. Nothing can go beyond the speed of light. So even though Alice and Bob are far apart, separate out, their results are correlated in a manner which is much stronger than what is predicted classically. Now let's look at this from another perspective. Anyone had a question here? Anyone would like to ask me something? Please try to do this as a homework. Right. So you could also email the results to me, or we could, at the start of the class tomorrow, we can look at your calculation. So I would like to give another example now of the same concept of non-locality, but in a different and an easier to understand manner. And the example that I would like to give is of Hardy's state. How quantum mechanics is truly non-local, it violates local realism. And this I'm going to show without having to talk about an inequality. The inequality, the Bell's inequality that we had in this case was 3 by 4. And we saw that it was violated. But this was slightly complicated. You had to do a lot of calculation and so on. So suppose I have a 2-qubit state, ket 0, 0, plus 0, 1, plus 1, 0. Now, if this is my 2-qubit state, what coefficient should I write that goes together with each one of these 3 qubits? If I would like to write one coefficient here, what should it be if the state is to be normalized? Can anyone respond?
1 over square root of 3.
Excellent. So because this ensures normalization. All right, so this is Hardy's state. So this is one way of writing the state, number one. Now let's do something interesting. Look at this term and this term. What I could do is I could factorize out Alice's. So this is Alice and this is Bob. Alice, Bob. Alice who owns the first qubit and Bob who owns the second qubit. So I factorize out Alice's qubit, which is ket 0, and write Bob's qubit, which turns out to be in a superposition of 0 and 1. And just for normalization, I'd like to write this as 1 over under root 2. So I need to put a 1 over under root 2 here as well. Okay, so this is just algebraic manipulation, manipulation of kets, if you would like to say. So then I need to write this state here, ket 1, 0. Okay, so I could write this as 1 over under root 3, ket 0. And instead of this state, let me write this state as ket 45. just by the diagrammatic representation. So if this were cat 0, this were cat 0, 1, sorry, then this state here would be cat 45 degrees. This is pi by 4. So this is cosine of pi by 4, 1 over under root 2. So I just write this combination here that I have in this green circle by cat 45 degrees. So plus I also need a, by the way, under root 2 or 3 plus 1 over under root 3, 1, 0. All right. So what I've written here is I've written the same state in a different form. The form 2 is the same as form 1. I've just done some factorization here. Let's write state number 1 in yet a different form, 1 over under root 3. And for that purpose, I focus my attention on the first term and the third term. And when I do that, I could write cat 0 plus 1 over under root 2 with another under root 2. This is the first term, which is a superposition of 0 and 1. The second qubit, Bob's qubit, is 0 plus 0, 1. So once again, I can write this as 2 over under root 3, 45 degrees, 0 degrees, plus 1 over under root 3, 0, 1, number 3. So now all in all, I have 3 different ways of writing the same quantum. Physically, all three are the same. So I have, let me rewrite 1 over under root 3, over under root 3, 0, 0 plus 0, 1 plus 1, 0. This is the same as 2 over under root 3, 0, 45 degrees plus 1 over under root 3, 1, 0. This is the same as 1 over under root 3, 0, 1 plus 2 over under root 3, 45, 0. So all 3 of these prescriptions or representations are for the same physical state, the Hardy state. Okay. Any any problems with this?
Sorry, number 3 equation has 1 0. Last ket is 1 0 or 0 1?
This one here?
The pink color.
Pink color. Yeah, 0, 1. Here, 0, 1. Okay, so this is 0, 1. All right. All
How
right.
is it 0 1? Sorry, I didn't understand. Isn't it 1 0?
No. So what I've done here is this term here, 0, 1. Second term
Oh,
here.
understood. Sorry.
Okay, okay. Now, if you look at these 3 ways of writing the same state, remember they are the same state. All 3 represent the same physical state. Therefore, if I were to do a measurement on the state, the measurement outcomes will be the same. If I did some measurement on this state or this state or this state, the measurement outcomes need to be the same. All right. Now what I would like to do, focus your attention on these 3 ways of writing the state. Now, what I would like to do is I have Alice and Bob, and I perform a measurement. Alice performs a measurement and Bob performs a measurement. Okay. And one measurement is that Alice does a measurement on the 0, 1 basis, Bob does a measurement on the 0, 1 basis. Okay. So what is the probability? Such kind of measurement, let's suppose I call it a Z measurement, capital Z measurement. What is the probability that the Z measurement on Alice and the Z measurement on Bob, that the Z measurement on Alice is, so all right, so what I would also like to do is I would like to assign outcomes. So if this outcome, this detector fires, the outcome is +1. If this detector fires, the outcome is -1. So what is the probability that if I that Z measurement on Alice, that is this measurement on Alice yields -1, and this measurement on Bob also yields -1. So what is this probability equal to? By looking at these states, either look at this state or this state or this state, could you tell me what this probability is going to be? So what I'm really asking is, Alice's measurement yields -1. So I'm asking the probability that this detector fires and this detector fires. This probability is 0. So can anyone else confirm or deny this?
I think it should be half, not 0.
It should be half. Well, let's see. If you look at this way of writing the state here, is there a cat1 term? In other words, is there a term of this kind? No, there isn't a term of this kind. So when you perform a measurement in the cat0, cat1 basis, so Alice does a measurement in this basis and Bob does a measurement in this basis. So Alice chooses this beam splitter and Bob chooses this beam splitter. There is no chance that this detector fires and this detector fires at the same time, right? So that's why I have an and here. So this probability is 0. Okay. So this means that classically, when we talk about our classical notions, this means that the particles that are with Alice and Bob, they do not have a projection on the one channel. They do not give an output which results in this detector triggering and this detector triggering both at the same time. Even though it's possible that for Alice, this detector clicks, and for Bob, but then for Bob, the other detector must click, because there are terms like 0, 1 and a term like 1, 0. It's also possible that for both Alice and Bob, the horizontal detector clicks. But it's not possible that for both Alice and Bob, the vertical detectors click. So this probability here is 0. All right. So this also means, now if everything is logical and everything is causal, which means there's a cause and effect relationship, this means that the particle, either Alice or Bob, must yield a result. Either of them must yield a result where the Z outcome is +1. There has to be a +1 outcome. All right. So if you look at these three terms here, there is, this would result in a +1 outcome on both channels. This would result a +1 outcome on Alice's channel. And this would result on a +1 outcome on Bob's channel. So there has to be at least one Z equals +1. All right. So let's find out the probability that if, let's find out the probability that if Alice's output is +1, what is the probability that Bob's output is +1? Oh, sorry. Now we would, okay, we would like to now find out the probability that if Alice does a Z measurement. Okay, now let's do the following. Alice does a Z measurement. So one output channel is cat 0, the other output channel is cat 1. This is Alice here. And this is Alice's beam splitter. And Bob's beam splitter is now slightly different. Bob's beam splitter is that one output channel is 45 degrees, the other output channel is 135 degrees. And if this detector fires, the output is assigned a value +1. And if this detector fires, the output is assigned a value -1. And this is called an X measurement. All right. So what is the probability that if Alice's measurement is +1 when measured along Z, what is the probability that Bob's measurement when measured along X is +1? So I would like to find out this probability here. And here are the three kinds ways in which I've written the state. So can you look at this equation here, this prescription here, number 2, and tell me what this probability is going to be?
2/3.
2/3. Are you sure?
If Alice is +1 on the Z and Bob is +1 on the X, right?
Right. So this is the relevant term. So when Alice measures along the Z, so when she performs this measurement along the Z, which is +1, then Bob's state is projected onto X, okay, onto 45 degrees. And the amplitude here is 2/3. So I take the square of this, I get 2/3. Is that correct? In fact, this is not correct, because the way I've written this expression is the following. I know that this is a conditional probability. What you mentioned is not a conditional probability. What you've mentioned is the probability of 2/3 is the probability of this thing. Okay. What I'm interested in is this probability, which is a conditional probability, which means that if this is the outcome on Alice's qubit, what is the outcome? What is the probability that Bob, when measures X, gives me an output +1? So could you now answer this question again? 1. Exactly. So this is now turned into a conditional probability statement, which means that if Alice measures her qubit to be in a state cat 0, then this entire state is being collapsed. it's being collapsed into and this term here is redundant. This state has to be normalized. So this is not required here. So this is the new state that is created. And when this new state is created, Bob, when measures along X, his state is 45 degrees. So in his case, this detector will always click with 100% probability. So this probability is 1. Likewise, if we were to compute now the probability, and now we would like to compute the probability that if we were to measure, so we know that either Alice or Bob, when they measure Z, the output should be +1 because they can't both be -1. That is the first condition that we've written. So if Bob measures Z and the output is +1, then what happens if Alice measures X? What is this probability going to be? That Alex measures X and her outcome is +1. So Bob is measuring +1 along Z, this thing here. So now we would like to find out the probability that X, a measurement of X by Alice gives 45. And in that case, this is always going to happen. The state is going to be collapsed into this term, and this probability is also going to be equal to 1. Now we have 3 conditions. We have looked at 3 statements. Probability that Alice and Bob both measure Z and the yield -1 is 0, which means that either Alice and Bob should measure 1 when they do a Z measurement. And when each one of them measures a Z measurement, the probability that the other party does an X measurement is always equal to 1. Now, from these 3 statements, can we predict what is the probability that if an X measurement is done by Alice and an X measurement is done by Bob, what is the probability that each one of them gets -1? Now, this is the most interesting question here. By looking at the results that we have, so how do we summarize the results? The results are summarized in the following fashion. Alice and Bob, when they measure Z, both of them cannot measure Z to be equal to -1. Therefore, either one of the Z measurements by Alice or Bob should yield a +1. And when they yield a +1, if X were measured by the other qubit, by the other party, it must yield a +1 because the probability is 100%. So can you tell me, by looking at these 3 statements, what is the causal inference? What is the most logical answer? Is there a probability that both Alice and Bob measure -1?
I think it will be 0.
Okay, I think you are thinking perfectly on the right lines. So just by causal inference, if causality is true, if one thing is true, it leads to another true thing. If that second thing is true, it leads to a third conclusion. And if all the conclusions are combined together, this is the statement that comes out to be true. That is, if both Alice and Bob measure their X qubits, it's not possible that both of them will get -1. And let me rephrase this. Alice and Bob have one particle each. If each one of them measures their particles along the Z basis, they can never get a -1 on both results at the same time, which means that one of them must give +1. upon a Z measurement. But we know that when one of them gives a +1 measurement along the Z basis, then the other one, when measured along the X basis, must also give a +1. This means that at least one of the measurements along X, when on the other party a Z measurement has taken place, must yield +1. So if one to do an X measurement on both parties at the same time, at least one of them must give you a +1. Therefore, it is impossible that when you do an X measurement on both parties, you get -1 on both of them at the same time, because that's not possible. So this is the causal relationship that classical physics predicts. Now what we would like to do is we would like to see whether this result is borne out by quantum mechanics. So we would like to find out this probability here using the rules of quantum mechanics and quantum computation. So our state is 1 over under root 2. And now we can write this state in whatever fashion we like. Let's write this state as, sorry, it's 1 over under root 3 ket 0 0 plus 0 1 plus 1 0. This is our Hardy state. We would like to find the overlap with, okay, can anyone tell me what do we want to find the overlap with if we would like to compute this probability quantum mechanically?
135 and 135.
What are we projecting along? So we're doing an, so
135.
we are doing 135, 135. Okay,
135.
exactly. So can I know your name, please?
Omar.
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 Right. Omar, thank you very much. So 135 degrees and 135 degrees. Because an X measurement really means a measurement along this basis. 45 degrees, 135 degrees. So an output of -1 means that we are projecting along this basis. And we want to find out this probability. So at the end, of course, you'd like to take the modulus square of this. So let's find out this probability. Now, in order to find this out, it's convenient to do the following. 135 degrees is, so this angle here becomes 135 degrees. Okay, so what we could do is we could write this as 1 over under root 2 ket 0 minus 1. Okay, so this is writing a quantum state in a different basis so that we can easily do the inner product. So bra 135 degrees would become, by the way, 135 degrees is the same as minus 45 degrees. Okay, it doesn't make much of a difference. So bra 135 degree would be 1 over under root 2 bra 0 minus 1. And by the way, you could also put a minus sign here and a plus sign here. It doesn't make any difference whatsoever. Okay. So if I were to compute this probability here, this 1 over under root 3, I just take out, it becomes 1 over 3, 135 degrees, ket 0, 135, 0, plus 135, ket 0, 135, ket 1, plus 135, ket 1, 135, ket 0, modulus square. So this is the result that I would like to compute. Now, just by looking at it, you can always do the algebra. It's not a big problem. 0 degrees basically 90 degrees. So ket 1 is basically 90 degrees. So you can find the overlap. So this is 1 over 3 cosine of 135 degrees. This is also cosine of 135 degrees plus cosine of 135 degrees plus cosine of 45 degrees plus cosine of 45 degrees plus cosine of 135 degrees. Add them up and square. Okay. Is this equal to 0? Is this answer equal to 0 or not? Whatever the answer is it equal to 0? Can anyone just tell me if this answer is 0? This answer is not 0. It's not 1, but it's not 0. It's of course greater than 0. It's a number greater than 0. By the way, if I were to make this substitution here, my life would be get slightly simpler. So I just plug in the values for 135, this thing in here. I can easily find out the inner products. But whatever the case is, this number is greater than 0 because neither one of, they're not 0. This is some
I guess
number. If I
it's 1
take
over
the square
6.
of it, I get 1 over 4 in over 3. 1 over 12 is my answer actually. And this is greater than 0. So even though classically by causal reality, the probability of having an X measurement on both Alice and Bob's qubit should not give me -1. Quantum mechanically, if I were to use a Hardy state, it turns out to be a non-zero, a finite probability. And this is why local realism is violated for this particular Hardy state. So this is the essence of non-locality. And this was the last topic I wanted to cover today. And I'll be talking more about quantum communication in the last lecture tomorrow. So I'm happy to take 1 or 2 questions. Sorry, it's been a slightly longer lecture because of the tedium and the cumbersome algebra involved. But do find out time to do the calculation about the probability boxes, which was the first example I took up this morning. So the essence of today's lecture is that with the help of quantum information and quantum mechanics, we can find out events. There is a finite probability of events which outstrips, which is higher than what is classically predicted. So strange results can appear which are classically forbidden, and that too without the need for local communication or superluminal communication is banned. We cannot transmit at messages faster than the speed of light. Even with this limitation, two objects that are really far apart, if they have been entangled in the past, they can give you measurement outcomes which totally defy the possibility of causal reality. And that's why we say that quantum mechanics is non-local. And some people say it's even non-real. So I can take 1 or 2 questions. All right. So if there are no more questions, maybe we'll meet tomorrow, inshallah, for the last class. And I'll give you one example from quantum communication, which is the BB84 protocol. All right. So thank you very much for all your time. And inshallah, we'll see you tomorrow. Ma salam and assalamu alaikum.
Thank you. Allah Hafiz, everyone.